The human body's ability to walk and run is amazing from an engineering perspective, and is very different from the abilities of the machines people build that move across land, most of which use wheels and other mechanisms, completely unlike biological systems. MIT professor Hugh Hare and fellow researchers are studying how legs work to enable locomotion in mammals, and how to incorporate biological principles and even animal-derived muscle tissue in machines in order to help rehabilitate the disabled and the elderly and to improve human locomotion.
About 8 million people just in the US alone desperately need technologies that will help them move again. I mean, just leg physical disabilities. Today in the United States, if a person suffers a stroke, they go to a leading research hospital, they'll be given a piece of plastic to treat their partially paralyzed ankle. To us, this is unacceptable. And we don't quite understand it because there's a billion-dollar market to be tapped here.
You have your foot like this, and literally your foot drops when it's in the air, and your toes want to stub on the ground. And so now to treat that, they put a plastic brace on that just locks your ankle at a 90-degree angle. And so the brace that was built in our laboratory has motion, and it has an actuator on the back, a motor, acts like the muscle, and moves the toes up and down. And so what it does is you wear something on your good leg, and you wear this device on your bad leg. And what it does is it watches the good leg and then performs the correct virtual muscle function to make the bad leg move in the right pattern.
For stroke or spinal cord injury patients, their limbs are paralyzed. So the idea there is either you wrap a robot around and you push on the human body, or you put implanted devices in the body and you take over the control of a person's muscle.
We want to understand how is it that we can control the mechanical response of a muscle using electrical stimulation. And the idea is if we can command a muscle to achieve a desired response, then we can potentially use that as an assistive or as a rehabilitative technology.
We're trying to couple the artificial devices to the neural system of the body. So probably 2 years from now, I will have devices implanted into my body called bions that measured the extent to which my spinal cord has activated my muscles in my biological leg. Those signals will be sent out to a robotic artificial foot-ankle system, and I'll be able to think and move my ankle.
And then you're taking advantage of the power of the human brain, because we know that we adapt so much better than computers do. So we could have a computer on this device and try to write a really good AI program, or we could just plug into the nerves and then the brain can do the AI for us.
That level of intimacy is very nice because now my artificial legs, first of all, they're passive, and I have no way of thinking and affecting my foot. My foot just sits there.
Which is really important. The major milestones, the way I see them, is first of all to be able to control animal-derived muscle in a petri dish. Then we can couple the information that we learned from those experiments with information or with knowledge in biomechanics and try to figure out how the two disciplines can result in a system that will enable the true generations of biologically realistic motions.
I believe in the next decade we will have artificial legs that are better than human legs for running. The best amputee runner for the 100-yard dash is only a second slower than the world record with biological legs. And that's just with carbon composite dumb passive springs.
And then I can come up.
That's very nice.
Isn't that neat? You guys have no idea. You have no idea, man.
Boy, going down is looking better and better.
You know that 2-year-old that makes their parents crazy? That's me.
So we'll see this gradual merging of the human and technology, and what will come out of that is a hybrid human that's actually better using certain metrics. As tissue engineering technologies progress, we can imagine eventually replacing various components of the prosthesis with biological materials. It'll be a future where when we architect a machine, we'll ask, for this component, should we use skin, or should we use steel or a composite? What should we use? Inevitably, I believe we'll end up with hybrid devices, because it won't always be optimal to use synthetic components, nor will it always be optimal to use biological components.